Take a look at this function. It's a fraction, and notice what would happen if we replaced x with 2. In the denominator, we would have 2 minus 2, 0. 2 times the 0 would be 0. The function is not defined at x equals 2, and yet we want to find the limit of the function as x approaches 2. Now, x approaching 2, that's an interesting idea. As x gets really close to 2, we want to find out what value f of x is approaching. And that's what limit is all about. So and the request for the idea is this, that the limit as x approaches 2, that's what this notation means, the limit as x approaches 2 of this is equal to what number? And all it's saying is, all this means is, let's take a look at the situation as x gets close to 2 and evaluate what the function is getting close to. What is the functional value getting close to? Now, there are several ways of finding a limit. A couple of ways are by looking at a table of values and by looking at a graph. We're going to do both of these now, and later we'll investigate some analytical approaches or some algebraic approaches to the idea. Let's take a look at a table of values right quick to get the feeling for this. Here's a table involving the previous function. In this row, I've got values of x. Now, just take a look in the middle of it. Here's 2. Here's our sort of our target point. And we are approaching 2 from values above 2 and also from values below 2. And that's the idea of the investigative process of limit. We are approaching the target point from both sides, and we want to know what value f of x is approaching from both sides. All right, so now notice in this row I'm finding f of x, and notice the values here. So I'm looking at, gee, as x gets close to 2 from the left, f of x is getting close to, well, let's see, 2.95, 2.975, 2.99. Gee, it looks like f of x is getting close to 3. And over here on the other side, as x gets close to 2 from numbers or values just above 2, just bigger than 2, then f of x is getting close to, well, let's see, 3.05, 3.025, 3.01. Well, again, f of x is approaching 3. Graphically, we can see it very clearly. This same idea is we can see very clearly by using a graph. It's the notion that as x is getting close to 2, the f of x is getting close to 3. And that's the investigative process of limit. All right, here's 2 on a graph. So as x gets close to 2 from the right, f of x is getting close to this 3. This is the level of 3 right here. And as x gets close to 2 from the left side, f of x, again, is getting close to 3. So we can say then that the limit as x approaches 2 of this function is 3. And yet, f of 2 is not defined. It just doesn't exist. This is one of the classic situations. I'm going to show you a number of situations involving limit. But the easiest situation is where the function is defined at the target point and the function is continuous at that point. Now just think of, we're going to define continuous a little more formally later, but continuous is as we would expect it to be. There aren't any holes in the graph if the function is continuous in a particular interval. Consider an interval, well, let's see. But let's find the limit as x approaches 0. As x approaches 0, same function. Let's find out what that is. As x approaches 0, come on over here. Here's 0. Now, as x approaches 0, as our value of x gets close to 0 from both sides, what is f of x approaching? You see, f of x is coming close to what value? Well, this value. You see, and it's pretty easy to figure out that value. The function is defined here. We could just take f of 0 and find that number. F of 0 is 2. That is, the point 0, 2 is on the graph. The function is continuous in this little interval, so it's very easy to calculate that limit to be 2. Here's another situation. You may be thinking now, well, gee, we have to, if we can find f of the target point, then that's the limit. Not so. Here's an example. Here's the same function, or a pretty similar function. I'm defining it in a couple of intervals, or in two pieces. F of x is what we had before as long as x is not equal to 2. But we're going to define f of x to be 5 when x is equal to 2. So here's what the graph looks like. You see, so the graph, or in this part of the definition, the function is undefined when x is 2, but we're defining x to be 5 when x reaches 2. So f of 2 is 5. But is that the limit? No, because the limit idea, the limit investigation is, what is f of x approaching as x approaches that target point? That's the idea. So once again, just like before, we're talking about as the x approaches the value 2, you see from both sides, f of x is approaching the value 3. Not this value, but the value 3. So still the limit is 3, even though f of 2 is not 3. That's okay. All right, here's a situation where the limit doesn't exist. And it's pretty easy to see why. Our target point, again, is 2. And notice that the function is defined on intervals here. It's a constant function on both of those intervals, but it's a different constant on this interval than it is on that interval. So it's pretty easy to see that as x approaches 2 from the left, f of x is approaching this level, and incidentally this is 3. So the limit as x approaches 2 from the left, and this is the notation for that idea, as x approaches 2 from the left of f of x is actually 3. But the limit as x approaches 2 from the right, well, let's investigate up here. As x approaches 2 from the right, you see f of x is up here at 6. So we're approaching the 6. So the limit from the right is not the same as the the limit from the left is not the same as the limit from the right, so we say that the limit itself generally does not exist. Here we have a graph, we have an asymptote, and let's say that this is our target point, and notice that when we approach the target point from both sides, as we approach from the right, f of x is going up without bound. As we approach from the left, f of x is going up without bound. So the function is approaching infinity as x approaches our target point. And that's another situation where the limit does not exist. Here's a list of all of the situations that we'll be discussing where the limits do not exist. Limits do not exist when f of x approaches different numbers from left and right. So when x approaches from left and right, we have different numbers for f of x. We looked at that just a little bit ago. And here we had a situation where f of x approaches infinity, and it's also true for f of x approaching negative infinity as x approaches the target point. So as x approaches target point, f of x is approaching infinity or negative infinity. In this section, we're going to look further at ways to evaluate limits. And it turns out that a lot of what we're going to talk about is really easy because often functions are continuous at the target point, and all it is a matter of taking f of the target point, and symbolically it goes like this. The limit as x approaches c of a function is just f of c. You see, if the function is continuous at that point. And for example, if we're taking the limit of this function, you see, of this expression, as x approaches 2, then take f of 2. Just replace the expression, in the expression, replace x with 2. We have 6 minus 5 or 1. So the limit then is 1. The limit as x approaches 4 of this means, what is f of 4? That is, put 4 in place of this x, and we have 4 and 4, 8. The cube root of 8 would be 2. And for this one, these are even more trivial. The limit as x approaches 7 of x, you see, f of x is x, so replace x with 7 and we have 7. And even more fundamental than that would be the limit of a constant. The limit as x approaches 7 of a constant would be the constant. I mean, after all, if you looked at the graph of this, it would be a horizontal line going through y equals 3. So as x approaches any value, the f of x is going to be 3. So these are rather trivial situations. Let's look at some others that are rather intuitive. Suppose we know that the limit as x approaches some target, the limit of our function as we approach the target is 7. Let's say that's given. We're not finding the limit, we're given the limit. Now, let's perform operations on this situation. The limit as x approaches c of 5 times f of x. 5 times f of x can be thought of as 5 times the limit of f of x. You see, the limit idea applies to the f of x. And so we just have 5 times 7. And that's what this is. That's all this is. This, the limit of f of x, you see, as x approaches c, is 7. So 5 times 7, 35. And the same goes with other operations. All we're doing is taking a real number and multiplying times f of x. But think about taking the square root of f of x. Well, the limit as x approaches c, you could think of this as, think of the square root out here as the square root of the limit of f of x. That limit of f of x is 7, so we get the square root of 7. And here we have the limit as x approaches c of f of x squared. Well, that's nothing more than, think of this bracket as being out here. You see, and all we would have is the limit of f of x, and all of that would be squared. So it's just 7 squared, or 49. Kind of an intuitive idea. Here's some more. Suppose the limit of f of x is 7, the limit of g of x is 4, and I'm not saying as x approaches c every single time. Let's make that assumption a little bit, because it's very repetitive to have to say it all the time. But the limit of f of x is 7, the limit of g of x is 4. Now, what about the limit as x approaches c of f of x plus g of x? You see, doesn't it make sense that if the limit of that function is 7, the limit of that function is 4, that this is just 7 plus 4? Sure it is. And so we could think of it as, we can kind of distribute this idea of limit through this bracket. So we'd say the limit of that function plus the limit of this function is what it's all about, so 7 plus 4, 11. And in a similar way, we could think of subtraction here of the two functions. We could think of multiplication of the two functions. If it was f of x times g of x, it would be 7 times 4. If it was f of x over g of x, it would be 7 divided by 4, 7 over 4, you see, for the result. Now, what about the composition? Well, that too is no big deal. The limit of f of g of x would be, now we're applying the limit idea to the g of x, and the limit of g of x, remember, was 4. So this is nothing but f of 4. And evaluate that, and we would find we would be resolving the situation. If it was g of f of x, we're taking the limit of g of f of x. We know that the limit of f of x is 7, so this is just g of 7, you see, and all of this is relatively intuitive. Consider the limit of this rational function, and we know that often with rational functions we have undefined values. If x takes on the value of -1, then this fraction is undefined. Now, in situations like this, this turns out to be not a continuous function throughout the domain of the function. That is, for every x, we don't have a spot on the graph, and all those spots aren't connected. We sort of have a hole in the graph here. And but the limit is still easy as long as the target point isn't the one that causes this rascal to be undefined. For example, if we're taking the limit of this as x approaches 0, hey, no problem. Our function is defined at that point. It's continuous in the neighborhood of that point. So all we do is find f of 0. Just replace these x's with 0, and we find the limit to be 1. In a similar way, the limit of the same function as x approaches 2, no big deal. Replace x with 2 in both places, and we find 9 over 3 or 3. But what happens if we're trying to find the limit as x approaches -1? Now here's where we run into trouble. You see, it's not just categorically true that if we have a function that is not continuous somewhere that we're going to have trouble. We only have trouble if that point where it's not continuous turns out to be the target point. But it's not something that we can't deal with. There are several ways to deal with it. Now, we looked at a situation like this graphically earlier, And if you put the graph of this expression on your graphing calculator, you would be able to determine the limit very, very quickly and easily. We want to find an algebraic approach to it. And there are two fundamental techniques to deal with this situation. One of the techniques is just manipulation. And the technique here is factoring. So we're just factoring in the numerator. This is the sum of cubes. We factor into a binomial times trinomial, and oh happy day, the binomials here and here cancel. And when they cancel, we have x squared minus x plus 1. Now what we have fundamentally done here is we have transformed by this calculation, and with this cancellation, we have changed our function, which is not continuous, into a continuous function. We are taking the limit of two functions that are equivalent except for that one point. You know, if you put both of these on the graphing calculator, they would overlap exactly except for the point that's undefined in this one. And so the limits as we approach that target point are exactly the same for these two. And so here we can just by direct substitution replace x with -1 and find that limit to be 3. Okay, so that's one technique, one situation. Here's the other situation. The other situation involves radicals. If, for example, we want the limit as x approaches 3 of this expression, notice if x is replaced with 3, we have an undefined situation here. When radicals are involved, jumpstart your thinking and the technique here of manipulation as being one of rationalization. Now, you've seen rationalizing before. You've heard the word before. It came up in situations like this, where you have an answer like, 1 over the square root of 5 minus 2, let's say, in a problem. And you're kind of looking for an exact value. You don't want to leave the radical in the denominator. So you rationalize by multiplying by the conjugate of this denominator. The conjugate is the same binomial with a different sign. And so we're multiplying by the square root of 5 plus 2 over the square root of 5 plus 2. Does that jumpstart your thinking about this? And in multiplying, it's helpful with binomials to put parentheses all around to help with the multiplication process. And when the smoke clears on this, we'll not have a radical in the denominator. We'll have a radical in the numerator, and we say that's okay. All right. Well, the technique is useful in clearing a radical from one part of a problem to another, from denominator to numerator, numerator to denominator. Here we're just using it as a manipulation technique. We're just trying to massage our expression, hoping that in the massaging process we're going to get a cancellation opportunity. And it turns out that we do here. We're going to rationalize the numerator. We're going to deliberately maybe create a fraction or a radical in the fraction and the denominator of the fraction, but we don't care about that. So what we're doing is this. We're saying, let's take this expression and multiply both numerator and denominator by the conjugate of the numerator. So we're multiplying by the square root of x plus 1 instead of minus plus 2. And we're going to do the same thing in the denominator. You see, we're just multiplying by a form of 1, which is what rationalizing is all about. We're not changing the value of the expression, we're changing its form. And that's what happens when we multiply by forms of 1. All right, so parenthesis will help us with the multiplication process all over the place in the numerator. In the numerator, let's see, we have the square root of x plus 1 times the square root of x plus 1. That's the square root of x plus 1 all squared, which gives us x plus 1. Then we know the middle term goes out because we're multiplying the sum of two numbers times the difference of the same two numbers, so we get the difference of squares. So we get minus the square of 2, which is 4. In the denominator, we're multiplying these two. Now I'm going to leave this in factored form. We could multiply this out, but I'm looking for a cancellation opportunity with this denominator because that's the troublesome part of the problem. So I'm going to leave this as x minus 3 times this other part. And now look at the numerator and think about a simplification. Sure, it turns out to be x minus 3. Oh, lucky for us. We get the cancellation as expected. And you know, with in algebra, you understood, and I hope you grabbed the idea that you should always be writing. That is, that you can see some ways to skip steps, but you need to resist the temptation of skipping steps. You need to, like, always be writing. If you're trying to think through and trying to skip steps, and you're thinking and not writing, then you're trying to skip too many steps. So here, let's see, we're canceling, and we have then the limit as x approaches 3 of this, which is all of this stuff. Now, by direct substitution, replace x with 3 in here, and we have, this becomes then three plus 1, or 4, the square root of 4 is 2, 2 plus 2, 4, this is 1/4. So that limit then turns out to be 1/4. Here's another situation involving some manipulation. The two classic situations, though, are the ones that we just had a look at. The first one had to do with factoring and canceling. The second one had to do with rationalizing a numerator. Other manipulations are just very straightforward. It's just a simplification of what we see in some way or another. Here's one example. The limit as delta x approaches 0 in this expression. Now, delta x, there's nothing mysterious about delta x. You may have seen the notation before. Don't worry about it. It's, I mean, it just is playing the role of any other variable, let's say, for our purposes right here. So we have delta x as a single entity. This is not delta times x, it's delta x. Okay? So as this amount approaches 0, what's going on over here? Well, our denominator is approaching 0, so we can't just deal with this by direct substitution. So we take the approach that we're going to manipulate a little bit. And to manipulate, we're expanding what we see, performing indicated operations, and just looking for opportunities to cancel. So 2 times x plus delta x is 2x plus 2 delta x. And we bring down the minus 2x. 2x minus 2x go out, so we have 2 delta x over delta x. The delta x's cancel, and we have a constant then. So we're looking for the limit as delta x approaches 0 of the constant 2. That is simply 2. Here's another manipulation situation. Kind of similar, but different in that we're using function notation. Here, f of x is defined to be 3x plus 2. And we want to find the limit as h approaches 0 of this. Now, you might recognize this as a difference quotient, and it just uses function notation, and we're manipulating with function notation. That's all there is to this problem. F of x plus h means in the f function, replace x with x plus h. So in this expression, replace that x with x plus h. So we would have 3 times x plus h plus 2. That's here. And then what does this mean? It means f of x. Well, this is f of x, so it's minus that expression. Now notice the introduction of the parenthesis to make sure we don't get confused with the sign changes here. And incidentally, let's back up a little bit. The need for the manipulation was that our target is approaching, our target point, 0, is causing the denominator to become 0. And that's the reason for us going through all of this process. All right, at any rate, let's see, 3 times x plus h, 3x plus 3h, bring down the 2, minus 3x minus 2, then 3x minus 3x go out, 2 minus 2 go out, and again, we have a nice happy situation with 3h over h. The h's cancel, so we have the limit of a constant, which gives us the constant 3.